Hi, this is Xiang. My colleague Yiming and I will give a presentation on our research work. The title of our presentation is Congestion and Timing Aware Macroplacement Using Machine Learning Predictions from Different Data Sources. The subtitle is Cross-Design Model Applicability and the Discerning Ensemble. In this presentation, we start with a brief introduction about machine learning solutions for macro placement. Then we discuss about our ML approach. On the ML technique side, we also explain our feature engineering method for cross-design predictions. In part 4, we explain our discerning ensemble approach. After that, we present our results on 3 different studies. Lastly, we present our conclusion.
The slides show the motivation of our approach. Macro placement makes big impact on congestion and timing. The 4 pictures shown in the slide are 4 different macro placements for the same design. The timing and congestion are post-optimization results. As you can see, the congestion and timing are very different among these 4 macro placement results. Because of this, we would like to use machine learning to predict post-optimization congestion and timing based on macro placement, and use the machine learning prediction to drive macro placer to find the best macro placement result.
But prediction solely based on macro placement is challenging. First, many tool options for placement exist for a variety of good reasons. Second, there are many different types of designs that a commercial EDA tool must support, including different technology nodes, meaning very different tool behaviors. Also, customers' various specific requirements for their IC layout, etc., have to be honored by the EDA tools. All these make it hard to develop an ML-based prediction system for commercial EDA tools. Nonetheless, recently, there are several active research works in applying machine learning, deep learning, reinforcement learning techniques in placement and macro placement. In our view, these works can be classified in 3 categories. First, enhancing the operations of traditional placement engines. And second, look ahead ML predictions for traditional placers. There's some work using ML to predict DRC hotspot and congestion map. And there are also some work on predicting scalar QR metrics, such as violence, congestion, timing, and power, etc. Our work falls into this category. And in category 3, there's some recent work using machine learning, deep learning, and reinforcement learning technique to create new placers that can replace traditional placers.
This slide shows how we collect machine learning training data to train the machine learning model. For each design, we create lots of different macro placements. Then we extract 65 pre-defined macro placement characteristics as machine learning feature. For each macro placement, we perform standard cell placement, physical synthesis, and global routing to get post-optimization timing and congestion result. The timing and congestion value correspond to machine learning labels. Each macro placement corresponding to one machine learning data consisting of feature and labels. After collecting the machine learning data, we apply machine learning to train the machine learning model to predict congestion and timing based on macro placement result. The 65 features we use are categorized into 3 different groups: design statistics, macro placement topology, and the macro grouping.
We develop our feature engineering approach for best cross-design result. All engineered features are evaluated for their feature importance scores for cross-design scenarios. The first scenario is one-on-one, using training on design A to predict design B. Another scenario is all-on-one, meaning using all training designs except the test design to predict the test design. The diagram here shows how individual features are ranked or scored given some pre-selected fixed features. In our study, all designs are rotated as the test designs exactly once. The ranking score is averaged from all rotations. This is the feature rankings result for the all-on-one scenario. 3 targets, violence, congestion, and TNS are used. There are several important observations. First, you can see the importance ranking is relatively flat across the features. Also, the ranking is quite similar even for different targets. For example, for all these 3 targets, feature 36, 26, 37, 25, etc., all appear in the top 7 or top 8 from these for 3 targets. The similar results are also obtained for the one-on-one cross-design feature ranking. Notice the top-ranked figures are almost identical for the 3 different targets. So top 7 here all the same. They are from feature 26, 37, 39, 28, etc. Also, these top-ranked features are similar to the top-ranked features in the all-on-one scenario in the previous slide. Here's the Disney visualization of feature data from 25 designs. The feature data has 65 features. With Disney, is reduced to 2 dimensions. It can be seen there's a little overlapping from different designs. We start our cross-design prediction investigation by looking at a baseline approach for 2 cross-design scenarios. These 2 tables shown here is a mean square root of congestion. The first table is one-on-one. The first column on the left is a training design. The top row is a test design. There are less than 25 by 25 one-on-one test cases with mean square error listed as table entry. The second table is all-on-one, where the top row is the test designs, with all the other designs used as training design, excluding the test design itself. Compare these 2 tables. A natural question comes up. Can we assign proper weights for different training designs in the one-on-one table so that the average prediction is better than all-on-one? But closely inspecting this problem reveals we'll need a way to match training designs with test designs without using any label information. Can this be achieved? These questions motivate us to invent a new discerning ensemble approach. Imagine we have a factory that can produce feature data. For macro placement, it's a placer that produces various placement. Also, we have a label factory that can produce the labels. For macro placement, it's the rest of the flow steps. Our theory is based on the following. Features, or observable states, and the labels all came from the same underpinning process, or processes that are closely related. That means there are features that are related to both X and Y. In the ML abstraction, observable state, which has redundant information, can be compressed as hidden states, which can then be decompressed back into the cleaner original state. The hidden state can be used for both supervised learning and reconstruction of the original feature. Now, if there is information loss during reconstruction from the hidden state to the reconstructed input, there are also similar information loss from the hidden state to the predicted label. So naturally, we can assume the ratio of training loss over reconstruction loss is close to a constant value. Then the training data and test data would have the same ratio too. Then from this fixed ratio, we can estimate the prediction loss without using any label. Similarly, bias term can be estimated as well. For more detailed analysis, please refer to our paper. Now, the basic idea of our discerning ensemble is simply this. We can use the projected loss or bias for weighting of the base learners' predictions. This would yield a different kind of ensemble technique, which we name it as a discerning ensemble. The name signifies the discerning power of base learners. It also rhymes with bagging, boosting, and staking, other types of ensemble. It was noting the weighting used in discerning ensemble is different from weighting used in staking, etc. Now, we apply our discerning ensemble approach to macro placement predictions. Here, every training design becomes a base learner in the ensemble. The projected loss or bias from the complete dataset X can be used for weighting. It also has advantages of good debuggability. For example, one can simply look at the best learners that has the highest weight to see if the training design is really a good match for the test design. If it's not, maybe this training design can be excluded, and data from the test design might be useful for further applications. Here, it shows the dataset for testing our ML approach. It has 72 designs, which forms 8 design groups based on their technology node and design style, etc. We devised 3 studies to evaluate the performance of our ML solution. In study 1, we pick group 3 from 8 design group as a test set. The reason we pick this one is because group 3 has the highest macro area to core area ratio, which makes it the hardest group to predict. In study 2, we randomly pick several groups to form a design universe. For example, you can pick design 1, design 3 as one design universe as all the available design in that universe, or we can just randomly select any of those available design groups. Let me look at averaged D1 design out predicting mean square error. In study 3, we compare our result with user manual macro placement result for 8 leading design. This is the result from study 1. The baseline is to combine training designs directly, and you can see their mean square error loss is about 2 times higher than the discerning ensemble result. This is for violence, congestion, and TNS. To be not affected by the choice of test design groups that we pick, we continue with study 2. In this study, we randomly select designs from the 8 design groups. In this way, we would have design universe of different size. Some cases, we only have a couple designs, and some cases, we will have close to 70 designs. So each dot represents the averaged mean square error from violence, congestion, and TNS. The result produced this very interesting plot that exposes the fundamental difference between the baseline approach, which combines all the training data directly into one data frame, and our discerning ensemble approach. It is obvious discerning ensemble has a smaller error range and a decreasing mean square error as more designs are included in the design universe.
This slide shows the timing and congestion comparison between our machine learning-based macro placement and the user micro placement for A industry designs. For example, for design 1, TNS and congestion of ML micro placement are much better than the ones from user micro placement. Overall, ML-driven micro placement achieve better congestion for all A designs and better TNS for 6 designs.
In summary, we have demonstrated proper macro placement predictions of QR for industry IC designs. The key factors that contributed to our success is 1. Large number of features that can capture placement states that affect downstream outcome, and 2. Feature engineering tailored for cross-design performance, and 3. ML data management, such as the discerning ensemble framework. Also, there are other possible usages of discerning ensemble for other EDA problems and other areas, such as a special purpose learning system, trusted machine learning, etc. We expect to see further research in this area. Thanks for your attention. This is the end of our presentation.